comfortably numbered, and this is my first ever YouTube video. If you do end up liking it, please consider liking it and subscribing to my channel. You all must have heard about the Rosetta stone, which is a stele that was found in Egypt in 196 BC that contained translations of the same story in 3 different languages. The third one, being Greek, helped decipher the ancient Egyptian languages. Would you be interested if I tell you that there exists a Rosetta stone in math, specifically in number theory? The original stone that was found in Egypt contained text written in both Egyptian hieroglyphics and Demotic script and also ancient Greek. In the mathematical variant, these inscriptions have been replaced by numbers and geometrical figures. This stone is intimately linked to one of the biggest projects in modern-day mathematics called the Langland's program. Langland's program, named after the mathematician Robert Langland, is also the grand unified theory of math because it touches almost every other mathematical discipline rather intimately. But what is this program about? Imagine 2 different lands, one of harmonic analysis and the other of number theory with the Rosetta stone on it. Langland's program is kind of like this bridge that connects these otherwise far-off lands and gives us a way to travel from one end to the other, revealing hidden mysterious structures that would have otherwise been unknown. So, what is harmonic analysis? It is this branch of math that deals with things like waves, symmetries, and surfaces. When I mention the word waves and symmetry to you, you should immediately be reminded of Fourier analysis, which is a field that takes up a periodic wave, that is a wave that repeats itself after a given time interval and breaks it up into its simpler sine and cosine components. 3Blue1Brown has an amazing video on Fourier analysis and I recommend you to go check it out in case you are interested. A link is attached in the description below. Sine and cosine functions have this amazing periodicity property, that is, invariance under translation by 2π. In simpler words, if you take a number x and move it towards the right by 2π units, the sign of the resulting number would be same as sign of the original number. Note that the input variable x here lies in the real number line. So what we have seen is that Fourier analysis tells us that sine and cosine waves are harmonics or basic functions on the real number line that build up all other periodic functions on the real number line. One can also ask, what are the harmonics of the circle? That is, what are the functions that build up all the other periodic functions in a circle? Those functions are exactly what we call modular forms. An example of a modular form is this function given over here. These rich and exciting structures are defined on the unit disk on the complex plane. And they possess mysterious and beautiful mathematical symmetries. Not just are they invariant under certain operations like the sine function, but much to a mathematician's delight, they have shown the most bizarre connections to some of the most unexpected areas of math. They have proved to be so ubiquitous that the famous mathematician Martin Eichler has this famous quote about how there are 5 fundamental operations in mathematics: addition, subtraction, multiplication, division, and modular forms. Now, let's talk more about number theory and eventually get to the Rosetta. To do that, we first discuss the theory of generating functions and modular arithmetic. Modular arithmetic first. Let's have a look at this clock, which we call the 12 clock. If I tell you that it's 11 AM right now and ask you the time after 2 hours, instead of reporting the answer as 13, you would tell me that it's 1 PM. Similarly, if I tell you that it's 10 PM right now and ask you the time after 11 hours, instead of telling me that the answer is 21, you would say that the answer is 9 PM. What you are doing is that after adding 11 plus 2 and getting 13, you are finding the remainder you get after dividing 13 by 12, which is 1. In other words, you find an integer x from the list 0, 1 to 11 such that 13 minus x is divisible by 12. So, 13 is equal to 1 and 0 is equal to 12 because 12 minus 0 is divisible by 12 and 13 minus 1 is also divisible by 12. We call this group Z mod 12 Z or the cyclic group of order 12. Now, what if in a hypothetical world you had 3 hours in the clock? Here, 1 plus 1 is 2 and 2 plus 1 is 3, which is 0 in this clock. We call this clock Z mod 3Z or the cyclic group of order 3. In another hypothetical scenario, let's imagine that our clock has 5 hours. We call this clock Z mod 5Z. Or, in a general scenario, suppose this clock has n number of hours. We call this clock Z mod NZ. To add a plus b, we find an integer c from the list 0, 1 to n minus 1 such that a plus b minus c is divisible by n. And we report the answer a plus b as c. Same goes for multiplication and subtraction. Now, in this cyclic group Z mod NZ, you can add, subtract, multiply, but can you divide? Let's consider the case when n is equal to 12. You can also write 12 as 3 into 4. Now, suppose you could divide every number with every other number in Z mod 12Z. We know that in Z mod 12Z, 12 is equal to 0, which means that 3 into 4 is 0. If you could divide by 3 on both sides, what you would get is this, which means 4 is equal to 0, which is an error. And this is not something that we want. So, should we lose all hope? Well, no, because the good news is that division is allowed for some integers, and those integers are primes. So if p is a prime, you can add, subtract, multiply and divide in Z mod pz, which we also call a finite field. It's called finite because it has a finite number of elements. Now let's focus on the objects that a number theorist is interested in. They are interested in polynomials and their integral solutions. An example of a polynomial is an elliptic curve, and an example of an elliptic curve is this equation given over here. We are interested in its integral solutions, i.e. points a, b that satisfy this curve such that both a and b are integers. An example of an integral solution is 1, 0. Because 0 plus 0 is equal to 1 cube minus 1 square. Now, if a, b is an integral solution to this curve, we let a, b undergo the process of reduction modulo p, which is also defined as follows. We find representatives of a and b in Z mod pz, that is, numbers a bar and b bar from the set 0, 1 to p minus 1 such that a minus a bar and b minus b bar are both divisible by b. The resulting tuple that we get out of this process is denoted as a bar, b bar. This is also called local solution for every prime p. This process of getting a bar, b bar from a, b is in words getting a local solution from a global solution. After we have gotten a local solution for every prime p from a global solution, we let it undergo another process, which is counting the number of solutions in Z mod pz, and we call the number of solutions Cp. Now, the number of solutions would be finite because Z mod pz is a finite field. After that, we let AP be the deficit in the number of solutions, that is, we define AP as p minus Cp. Let's run this process for a curve y square plus y is equal to x cube minus x square and p is equal to 3. Any solution of this curve in z mod 3z can be one of these. Let's check which one of these are actually solutions to this curve. What about 0, 0? Well, yes, that is a solution because 0 plus 0 is 0 minus 0. Is 0, 1 a solution? The left-hand side of this equation looks like 1 square plus 1, which is equal to 2, whereas the right-hand side looks like 0 cube minus 0 square, which is 0. Since 2 minus 0 is not divisible by 3, 2 is not equal to 0 in z mod 3z, so this is not a solution. Is 1, 2 a solution? The right-hand side of this equation is 2 square plus 2, which is 6, which is equal to 0 in z mod 3z because 6 is divisible by 3. Whereas the left-hand side is 1 cube minus 1, which is 0. So 1, 2 is a solution. At this point, I would encourage you to try these yourself. Here are all the solutions and non-solutions marked. Once we have this, we can calculate our numbers CP and AP. CP, which is defined as C3, is equal to 4, and AP is P minus CP, which is 3 minus 4, which is equal to minus 1. A random fact. A field is a mathematical structure where you can add, subtract, multiply, and divide. What we have seen is that Z mod PZ is a field because you can divide here, but Z mod NZ is not. But what if I need to know what AN looks like when n is not a prime? For example, what does A42 look like? And definitely I do want to know the answer to that because 42 is the answer to the ultimate question of life, the universe, and everything. Well, it's still not a problem. Even when you can't divide in Z mod NZ, you can still find the number of solutions in that ring very easily. AP carries useful information about the curve y square plus y equal to x cube minus x square, precisely the number that measures the failure of the number of solutions from being p. But if you ask me to evaluate for all p, I would want to bang my head against the wall. But luckily, we can ask a computer to blurt out AP or wish for the existence of a mathematical theory that would give us AP for all p. Why not try to build that theory? To do that, let's talk about generating functions. The best way to learn the theory of generating functions is through Fibonacci or Hemachandra numbers. The zeroth Fibonacci number is 1, the first Fibonacci number is 1, the second Fibonacci number is 2, the third Fibonacci number is 3, the fifth one is 5, the sixth one is 8, and so on. If I denote the nth Fibonacci number as Sn, then a pattern that I observe here is that Sn is equal to Sn minus 1 plus Sn minus 2. The first few Fibonacci numbers are written over here. Now, I define this function f of x, which is s0 plus s1x plus s2x squared all the way to infinity. We somehow want to use this expression over here, which is Sn is equal to Sn minus 1 plus Sn minus 2. To do that, we first construct this function xf of x, which we can write as s0x plus s1x squared plus s2x cubed all the way to infinity. I can also write it as summation Sn x to the power n plus 1, where n is greater than or equal to 0. If we let our n start from 0, n plus 1 starts from 1, so we can also write the sum as summation Sn minus 1 x to the power n for all n greater than or equal to 1. Similarly, x square f of x is defined as s0 x squared plus s1 x cubed all the way to infinity, and this in a similar way would be summation Sn minus 2 x to the power n for n greater than or equal to 2. If you subtract x f x plus x square f of x from f of x, you will get 1. A simple looking description of f of x is 1 upon 1 minus x squared. From our identity that we learnt in school, which is 1 upon 1 minus a is 1 plus a squared plus a cubed all the way to infinity, we get that f of x is equal to 1 plus x minus x squared plus x minus x squared squared plus x minus x squared cube, and so on. If we write the power series expansion of it, that is, collect the coefficients of x to the power n, we see that the Fibonacci numbers appear. What we have seen is that f of x is a good representative of the number Sn. This inspires the notion of a generating function, which is a function whose Taylor series coefficients gives us values of a sequence. I'll quickly remind you of the sequence AP that we had constructed previously. An interesting question to ponder over is whether we can have a generating function for AP, and the answer is yes, and we can say much more. What we can say is that the generating function for AP that we get is actually a modular form. And the generating function for AP is this function given over here, which is defined by f of q. Expressing this in terms of power series, we get this expression, which we can also write as summation bn q to the n. A few values of bn are given as follows: b2 is equal to minus 2, b3 is equal to minus 1, b5 is equal to 1, and b7 is equal to minus 2. And it is rather surprising that an is equal to bn. Also, f of q is a modular form. F of q very much behaves like sin x and cosine x and other trigonometric functions. Just like sin x is invariant under translation by 2 pi, f of q is invariant under the operations of the circle that exchange one of the triangles with the other. And yes, such operations exist. And for any two triangles in the figure, there exists a transformation of the unit disk that transforms one triangle to the other. And a function is invariant under all these transformations. That is why f is a modular form. So we have seen that an elliptic curve, which looks like this, has these numbers an attached to it for every n, and these an produce a modular form, which is an exquisite function with its beautiful symmetries and patterns, and it lies in the realm of harmonic analysis. And we can do this for every elliptic curve. What that means is that every elliptic curve, that is a curve that looks like y squared equal to ax cubed plus bx plus c, comes from a modular form, which means every elliptic curve is modular. This is the famous Shimura-Taniyama wave conjecture in math. In fact, one can say more. For every modular form of a certain kind, you can associate an elliptic curve. This is a surprising connection because even though modular forms have been bewildering objects in their own right ever since they were discovered, it took more than 100 years to find out how useful they can be in the world of number theory. Now let's quickly talk about the Rosetta stone that we mentioned in the beginning of this video. We have seen that we are interested in elliptic curves and their integral solutions. So the top occupies one part of our trilingual stone. The third is being occupied by solutions over finite field. What is this second row for though? If you take an elliptic curve and look at its complex solutions, that is solutions of the form a comma b, where both a and b lie in the complex plane, the graph that would result out of this would be a surface that looks like a donut. A donut is a kind of a Riemann surface, and so the second row deals with a branch of mathematics called Riemann surfaces that initially seem to have no connection with number theory. You might wonder, why on earth do we care about elliptic curves? That's a fair question, and the reasons are endless. However, I'll just mention two of them here. First is that they were fundamental objects in Wiles's proof of Fermat's last theorem, a problem that remained unsolved for 350 years. Second, modern-day cryptography is almost impossible without elliptic curves, specifically solutions of elliptic curves modulo prime. For example, the WhatsApp encryption algorithm uses the theory of elliptic curves. In summary, we have built this land of number theory and this land of harmonic analysis, and each of them have their own interesting objects. Langland's program is a way to create a bridge between them that helps us travel from one end to the other. I must mention at this point that most of these present-day connections are conjectural, that is, skeptical, but they are rooted in already proven strong foundations such as the link between elliptic curves and modular forms. Mathematicians working on this program are trying to build these connections bit by bit. It's almost like we have this big giant object of theory that is casting its shadows on the number theory wall and the harmonic analysis wall. We don't understand what this giant object looks like, but we have a vague understanding of what these shadows look like. Langland's program is a way to build up this object bit by bit. That is why Langland's program is also called the Grand Unified Theory of Math, because there is hardly a mathematical discipline it does not sweep as it walks in this giant mathematical world like a big monster. It is beautiful how almost in a stroke of black magic, this program weaves a delicate tapestry of numbers, symmetries, and equations.